we have seen that in the momentum space, we have a very similar representation. So from the psi in terms of x, in order to convert that into the momentum space, is basically the Fourier transform. And in order to convert from the momentum space to the position space is basically the inverse Fourier transform. This is something we have learned. So what I'm trying to drive at is that the whole formulation of quantum mechanics that you have learned in the position space can also be formulated in the momentum space. And you have seen that in that case, the Schrodinger equation becomes I h cross L del t of p t, that will be equal to same p square y twice n, and it would be phi p t plus phi and phi. This is actually, the whole thing is actually Vx applied on, sorry, this is actually Vx applied on psi x, its inverse Laplace transform. Okay, this thing. So you can see that you can write the whole thing in terms of the momentum, but you need now to understand what is the x operator and what is p operator in the momentum basis. Okay, so this is something that we need to work out. Now, in order to work out that, again, I need space, so let me clear it up. Therefore, the Fourier transform of this should give the equivalent operator in the p basis. So, basically, then the Fourier transform of x psi x should give it will be x operator in p basis, and this will give us what is the x operator. Okay, so let's try to do that. So x operator in p basis phi p is then the Fourier transform of this. So it is 1 by root over 2 pi h cross integral minus infinity to infinity. It is x psi x e to the power minus I dx by h cross dx. And then we need to calculate this. And in order to calculate this, what we'll do, I'll keep this one up front and multiply here. So it will be 1 by root 2 pi h cross minus infinity to infinity. I'll take psi up front, psi x, and I'll put this one in bracket, x e to the power minus I dx by h cross dx. Now it is easy to see what this bracketed quantity is. I'll do it here. If you see del p of e to the power minus I px by h, then it will be minus ix by h cross minus ix by h cross, and then the same thing, e to the power minus I px by h cross. So x times this is here, we now understand that this is nothing but this term goes to this side, and let us write it that way then. It is so I'll just close this and put it this way. 1 by root over 2 pi h cross. Here, minus infinity to infinity. It is psi x. Now this one I will just substitute. It will be minus h cross by I del p of e to the power minus I p x y h cross. Okay, I'll hide this. Yeah. This one is actually IH cross, so I can bring that forward. IH cross. This is 1 by root 2 pi h cross. It is minus infinity to infinity. Now I can, since this is not dependent on p, I can put it here. It is del p of psi x times e to the power minus I p x by h cross, this whole thing, okay, is equal to, now I can see I h cross by root over 2 pi h cross from here, and then I can exchange the positions of the integration and differentiation. So it is del p integral minus infinity to infinity. This is psi x e to the power minus I p x by h cross dx, and this is something that we know. We know that this is nothing but, including this, is nothing but I h cross remains from here, and it is del p of phi p. Okay, so what is the left hand side? It was phi p. So x operator operating on phi p is I h del p. So this gives x operator is nothing but I h cross del p. Notice that there is a difference between what you did in the x domain and what you are getting in the p domain. In the x domain, the p operator is minus I h cross del x. While in the p domain, x operator is I h cross del p. There is a minus missing here. Just keep that in mind. So there is a bit of difference between the two representations. Okay, so just note it down because this is something that you will need to use later. I have to kill it and we have to go on. Now we need to know what is P operator. So P operator in the x domain, it was minus I h cross del x operating on psi. Again, in order to take the Fourier transform, 2 pi h cross minus infinity to infinity, it is this term I have to write minus I h cross del x close psi x. In order to take the Fourier transform, it is e to the power minus I p x by h cross del x, so dx. This is right here. So that space. I'll bring the IH cross up front minus IH cross. Then I have this, so I'll better write it down. It will be easier for me to write. Minus IH cross divided by root 2 pi H cross. And this one is then integral minus infinity to infinity del psi del x del psi del x e to the power minus I px pi h cross dx. All right, now you see here, this is the thing that I have to integrate, and it is easy to integrate that by parts. So integrate this part by parts. What you get is, I'll just write this one here. This is what we are doing by parts. So this one, if you integrate by parts, it gives minus infinity to infinity. I will first differentiate this one. So it is del x of e to the power minus I px by h cross psi dx, and then there will be plus psi e to the power this term minus I px by h cross. This is computed from minus infinity at minus infinity and infinity. Now this is definitely 0 because psi goes to 0 at the both ends. So this term is 0. So we end up with only this. Now we can write p hat phi p is equal to, सामने क्या था? This was the thing in the front. Minus I h cross root 2 pi h cross, and we had another minus here, minus. So this minus and this minus will cancel. This will become plus. It will be minus infinity to infinity integral. It is, if you integrate this, if you differentiate this with respect to x, you get minus I p by h cross. It will be e to the power minus I p x by h cross psi dx. Then I will get this term outside. It is it will be I h cross by root 2 pi h cross, and this one will come out minus I y h cross. It is differentiation with respect to x, so I can take out root p also, I p by h cross, and it is then you have integral minus infinity to infinity. What remains is nothing but a Fourier transform of psi e to the power minus I p x by h cross dx. So this is equal to I can see that minus I minus, so it gets plus, h cancels off, so effectively it becomes p times pi. Simple. So the way in the x domain, x basis, x operator was multiply pi x. In the p basis, p operator is nothing but multiply by p. Okay, in the problem that I gave in the last tutorial, since this was not told in the class as yet, you could have kept it in terms of the operator p, or in place of the operator p, you could have simply put the p and then solved it. Both are okay. Now, so let us summarize what we have learned in terms of working in P basis. I will just erase this and we have to continue with that. Yeah. In the P basis, we have additionally learned today that the X operator is nothing but it is I H cross del P, and P operator is nothing but P. So now the whole grounding is laid. You can see that the way you can solve a problem in the X basis, you can also solve a problem in the P basis. In order to convert a psi function from the X basis to P basis, all you have to do is to take a Fourier transform. You can write the whole Schrodinger equation in the P basis. You can have the expressions of the operators in the P basis, and you can solve everything. When would you like to do that? There are two situations in which you would like to do that. First, if your question concerns P, that means normally if you ask the question, what is the probability of finding the particle in this part of the space, then if you are asking a question related to the spatial distribution of psi. And if you are asking a question related to the momentum distribution of psi, that means the psi function expressed in terms of the momentum, so some kind of a functional form, so psi, then, well, I'm drawing a real number, but it could be a complex number. Then basically you're saying that suppose I go from a point to a value B, A and B are values of the momentum, then what is the probability of finding the particle having a momentum within this range is nothing but the area under this mod psi square in this range, integrated over this range. So if you are asking a question related to the probability of finding a particular range of momentum, then you need the psi expressed as a function of P, and then it might be easier to do the whole problem in the P basis. There's another issue. The issue is that if you look at the Schrodinger equation, it has a P square by twice M term operating on psi plus a V term operating on psi in the right hand side. Now in the X basis, this term is a double derivative of psi. This term depends on the form of the V function, but that is the form, whatever the functional form, that is multiplied with psi. So you essentially get a second order equation in the right hand side. In the P basis, this is nothing but P multiplied to psi. So P square multiplied with psi. But V will have X in it, and each X has to be written in form of this, and therefore if it is a quadratic form in terms of X square, then you will get a double derivative. But if it is in the form of a linear function of X, something that happens in a potential well, something like this. If the potential well looks like this, it is a linear function of X, and in that case, in the right hand side, you will get a first order form, which is easier to solve. So these are the situations in which we do use the P representation of this. Okay, so at this stage, I'll stop and I'll invite questions, and we'll have some entertainment, and then I'll go to the next topic. So let's briefly stop, and if there are any questions, ask at this stage, and then I'll go ahead. Does anybody have any question on whatever I taught? So the basic, yeah, come on, brother.
So for suppose if there are constant potentials, then in general what we used to do with these differential equations was we used to treat them as time independent ones, and then equate the left hand side to a particular constant and the same constant with the right hand side. Suppose if v is a constant, we don't have to do that anymore, right?
Yeah. V is a constant is a very special situation where it's a free particle. But if V is not a constant, something like this or something like that, then you will have to substitute the functional form, right? V is a function of x. And then when you write that as an operator, these are operators. When you write that as an operator, you will have to substitute this, right? So if it is a constant, then obviously this will not matter. It's just a constant value. X doesn't appear
Yes.
in this case, right? It doesn't. It's
Yes.
not a function of x. Therefore, it's just then a constant multiplied by psi. It will be very simple to solve the way you solve the free particle equation.
Thank you, sir.
Any other question?
Sir, I have question regarding tutorial question.
Hello.
So in question number 2, part C, we are asked to transform the operators in the terms of eigenvectors.
Yeah.
So there we are using the projection operator on the the matrix or operator. Yeah. So what does that physically mean? Like, how are we projecting an operator? Like, what happens?
No. You can project a vector into another vector. You cannot project an operator into another vector. What actually you are doing is that when you are changing the basis, the operator itself changes, because whatever the operator was doing in one basis, when you change the basis, the operator should do the same, and therefore the matrix form of the operator should change. So it is not that you are taking the projection of an operator in the new basis, but you are expressing the operator in the new basis so that it does the same job.
Okay.
Any other question?
Excuse me, sir.
Yes.
So, what do you mean by two matrices are simultaneously diagonalizable? It was in the tutorial problem.
Yes, I have done that. Simultaneously diagonalizable happens when they commute. So I have shown that if these two matrices commute, then they will have simultaneous, or they will have the same eigenvectors. So if they have same eigenvectors, you can always define a new basis comprising those orthonormal eigenvectors. And if you define that, then both matrices will become diagonal. So two operators can simultaneously diagonalized if they commute with each other.
Sir, but if one of them is a degenerate matrix, means they do not have all the common eigenfunctions, only some of them are common. In that case, we can't say that they are simultaneously diagonalizable,
No.
right?
In that case, what will happen is that there would be some eigenplane. So there will be an eigenplane associated with the common or the repeated eigenvalues. And that eigenplane will contain all the vectors, all the eigenvectors, right? All the vectors in that eigenplane are eigenvectors. Then I said that you have to create two orthonormal eigenvectors by Gram-Schmidt orthonormalization procedure. Now that can be done in both the operators. Okay, so
Right.
So you can the vectors there will be the theorem that I proved in the class says that there will be at least a set of common eigenvectors. But in the case of a repeated eigenvalue, what happens is that in that plane all vectors are eigenvectors. We will not choose them, but there will be at least one set, that one set of eigenvectors that are common between the two. That's what the theorem says. Well, what I will do now is that for the last few classes, I was talking in terms of, let me erase this. for the last few classes, I was talking in terms of matrix representation of vectors and operators and things like that. And it might look like a sort of piece of information to you. What is the use of that? Today we'll talk about the actual use of this matrix representation, how to actually use it to solve problems. Firstly, these are mainly used in order to numerically solve problems. And since you know computer programming reasonably well, it will be very interesting for you to actually learn how to solve problems in quantum mechanics, not just by integrating by hand, but also by numerical methods. So in this case, just consider that you have the x coordinate. Here is my 0, and say that beyond a certain range, the psi function becomes practically 0. So this is some large value, minus value, this is some large plus value. Now we can divide this space into a finite number of divisions. Okay, here also. So this one can be -1, -2, -3, 1, 2, 3, and so on and so forth. Now, the psi function will then be defined in terms of these positions. So at this particular position, what was the psi function? At this particular position, what was the psi function? So on and so forth. So psi will be available then as a column vector, looking like this. So this is psi at the first position, psi at the second position, and so on and so forth. Remember, this column vector with elements can become complex numbers. These may be complex numbers in general. So when you say that I start from an initial psi function, initial wave function, then that initial wave function is given as a column vector like this. Each one is a psi defined at these positions. Okay. Now we need to write down the Schrödinger equation, and Schrödinger equation involves the x operator. X operator. What will be the x operator in this basis? See, these bases are essentially at the basis vectors are 1, 0, 0, 0, 0. Again, another one is 0, 1, 0, 0, 0, 0. All that I have already talked about it. The question is that these are the basis vectors. How would you define the x matrix? I'll write it below because it will be a square matrix. X. So it has to be then a square matrix because it converts a vector, n-dimensional vector, the dimension given by how many divisions we have divided it into, and it has to be a square matrix. Now just repeat what I said, that the x coordinate can be divided into a few subdivisions. The way you solve any differential equation solving problem, you essentially take steps. So here x is divided into a few subdivisions. In the computer, you can divide it as many as possible. All that will happen is the size of this vector will be larger. So at every of this point, the psi will be defined. That means the psi function will have a value at every point. I'm drawing it as a real valued thing because I cannot draw a complex number. But at every point, a complex number will be defined, right? And these are those values. So psi 1 is a value of psi, complex number, at the first point. Psi 2 is a value of psi at the second point, and so on and so forth at the end point. So the moment you have defined this function is completely defined, at least at those. And if you then communicate to somebody this particular set of complex numbers, he will be able to construct the complex valued function. So the complex number, the psi, initial psi, can be defined as a column vector like this. Now we need to solve the differential equation, the Schrodinger equation, and for that Schrodinger equation contains the P matrix, the X vector, and so on and so forth. So X as an operator, its role, its job is that when it operates on a psi, it multiplies X with psi. So we need to construct this square matrix in such a way that its effects will be this, and that can be done by so I'll write it X psi. Then I have to write here this function psi 1, psi 2, psi n. So see, when you multiply that, this one gets multiplied with this one. That means its position, X value, gets multiplied with psi 1. X value, the second position, gets multiplied with psi 2. X value, the third position, gets multiplied with psi 3, so on and so forth. So X matrix is nothing but, now I'll just erase and write it properly. Your X matrix is nothing but x1, x2, xn, and the rest are zeros. Simple. Okay. Now in the this will appear in the V function, right? In the V function, we'll have this operator, and that is have to be what has to be substituted by this. And for example, if you have V as half kx square, as in the harmonic oscillator, it will be half k. It will be x1 square, x2 square, xn square, and rest zeros. So this is the way to write down the V function if your potential is a harmonic oscillator potential. But if it is some other potential function, you can easily see how we can write the function in terms of x operator. Good. Well, now I need to clear up because today I am not using a larger canvas. You also need to write down p square by twice m, right? And this is h cross square by twice m del 2 so effectively we will need to write down the double derivative as a matrix. This is a constant, so I don't care about it. This is a double derivative we need to write down as a matrix. How do we write down that as a matrix? Now notice, you had probably learned in the numerical analysis course that the double derivative, double derivatives of some function is by the finite difference technique. It is u x plus delta x minus twice u of x plus u x minus delta x divided by delta x. This delta x is, as I said, along the x coordinate. I have divided into parts, and this is the delta x. So x plus delta x, suppose I am talking about this particular term, a particular term in the, for example, if I am talking about this particular position, then the position of whatever we are trying to calculate, this one is the next one, and this one is the previous one. So what does this do if you use a finite difference formula? This formula has to be written in terms of a matrix. So you see your 2 del x2 becomes, if you think in terms of that matrix, it becomes, suppose I'm talking about this particular term here. That term will be multiplied by minus 2. So here it will be minus say this is applying on a psi function. Sorry, line drawing is pretty bad. Psi 1, psi 2, psi n. Now I'm talking about a particular term in between here. This is minus 2 times this, and then I have to also put here and here. These are the off diagonal terms. This will become 1 and this will become 1. And this will continue. Therefore, all the diagonal terms will become minus 2. And all the off diagonal terms, the first term will be 1. And the rest are zeros. So do you see how the second derivative can be represented in the matrix form? So in that case, the diagonal terms will be the minus 2, and the first off diagonal terms will be this side and that side will be 1 because of this particular formula. And the whole thing will have to be divided by delta x square. So it will have to be preceded by 1 by delta x square. That's all. So this way you can see that when you write the Hamiltonian operator, it will have a p square by twice m Hamiltonian operator operating on psi. I'll write that way. Psi is operating on psi plus v operating on psi. Now v, I've just illustrated how this can be written as a matrix. This can also be written as a matrix, and so we can write the whole thing as a Hamiltonian matrix operating on psi. And what will that Hamiltonian matrix be? It is basically p square by twice m plus v. So you have the p square by twice m will contain the h square by this one. Sorry, h square will come from. My point is just this: that there is some constant multiplied, and this matrix for the del 2 del x2 term is like this. Plus there will be the v term, which will have the diagonal term filled up. So effectively, you will be able to write down, because you know how to add matrices, square matrices, you will be able to write down the Hamiltonian as a square matrix. Okay. Now, if you have written the Hamiltonian as a square matrix, you know that in the time-independent Schrodinger equation, the eigenvalues of the Hamiltonian matrix, Hamiltonian operator, are the energy values that you can see. And if you have a square matrix, you can easily obtain its eigenvalues. So that is how you can obtain the energy levels that can be seen, that can be observed. For example, in the harmonic oscillator, you know that n plus half h cross omega are the energy levels that you can easily obtain by simply obtaining the eigenvalues of this matrix. What will the eigenvector signify? Eigenvector will signify the eigen functions. Eigenvector will give a column like this, and each value operated on each of these positions, taken at each of these positions, will give a function, and therefore the eigen functions can be obtained by the eigenvector from the eigenvectors. And you will check whether you are getting that or not. You get the point? Have you understood how it is to be done? Is there any question on this? Is there any question on this?
Sir, please could you repeat the last line?
This is something that you will have to do in the next assignment. That's why
Sir, could you
everything
please,
clear. Yeah.
sir,
Again?
could you please repeat the last part, the eigenfunction part?
Yeah. Sure. Okay, let me erase this and let me write this again then. So I've just illustrated how to write the Hamiltonian operator as a square matrix. Okay. Then from there, the eigenvalues of this square matrix you can easily obtain. These are the energy values. Huh? Okay. The eigenvector eigenvectors will come like vectors like this. Say some. This value, again, you think in terms of the position coordinate. This is the value here. This is the value here, so on and so forth. These are complex numbers, but I'm just illustrating how this is to be done. So ultimately, you get joining them a function. So that will then be the eigenfunction. This way, you will obtain the different eigenvectors. You know that eigenvectors. The ground state eigenvector will come. Eigenfunction will come like this. Fast excited state eigenfunction will come like that, and so on and so forth. You know that you have already done that. This can also be obtained as these eigenvectors. Okay. Now the issue is that if you want to calculate the psi as x and t, then these are the C1 psi naught e to the power the phase factor minus I e t by h cross. This e is that specific eigenvalue, so I'll do it better. C naught plus C1 psi 1 e to the power minus I e1 t by h cross, and so on and so forth. So now you have the initial wave function whose projection on the first eigenvector will give C naught, whose projection on the second eigenvector will give C1, and so on and so forth. So you can determine numerically this projection can be easily calculated because it's an overlap integral. You can easily calculate it numerically. Psi naught, psi 1 are calculated this way, and the eigenvalues are calculated. Therefore, E naughts are known. All that you need to do then, in order to calculate it at some later time, is simply calculate these, and you'll find that in most cases, after some terms, the C become so small that you don't need to consider it. Maybe 4 or 5 terms. And after that, you don't need to consider that. So the solution of the differential equation can be easily obtained numerically using this matrix method. And all the operators can be written as matrices. Okay. Any questions on this?
Sir?
Yeah.
So when we solve the problems in actual position space, we see that energy has infinite number of eigenvalues.
Yes.
But in this case, the Hamiltonian being a finite square matrix, there are only finitely many eigenvalues. So I'm asking which ones do I get from the matrix?
Yes, you will get the first few. That means depending on the subdivisions that you create, depending on the number of subdivisions that you create, you will get as many eigenvalues. And in order to go to higher order eigenvalues, you need to create far more subdivisions.
So it is
Depending on,
always first
normally you
few
will
from the
divide
down.
the space. If you are doing in a computer, at least 100 eigenvalues can easily be obtained. Any other question? Okay, so the next assignment for this week, it will not be a tutorial, it will be an assignment to be done on a computer. You will write, you'll do it for the system that you already know, the harmonic oscillator. Because then you will get the results and you will be able to tally with what you already know analytically. But now notice that the difference between one system and another is essentially the V function. And the V function can now be written as a matrix. So it is very easy to do this problem for any arbitrary given potential function. All that will happen is the elements in this matrix will change. As a result, the eigenvalues will change. As a result of it, the eigenvectors will change. And still, the result will be a combination written like this. Okay. So, this is if you once write it correctly for the harmonic oscillator problem, that will work for any given potential function. So your task the next week will be to write this program for the harmonic oscillator by dividing the space, for example, say from the left hand side to the right hand side. I'll have to give you some range after which it practically becomes 0, maybe say minus 30 to 30, I don't know. So, and divide it into 100 parts. So define the x position of each part, and then the x vector, x operator will be those position numbers in the diagonal elements, and do it that way. The next day we'll go into angular momentum and spin. But angular momentum, how much have you done? Should I have to treat the usual angular momentum in quantum domain and then go into spin, or you already know about the angular momentum problem? Can somebody just unmute and tell me? I can assume that you already know the angular momentum, the operator corresponding to angular momentum, the fact that the operators for the x coordinate, operator for the y coordinate do not commute with each other, and what the commutators are, those things you know. No. Can somebody just clearly state whether you know already or do I have to repeat? That's the issue.
The things that you have stated, we know this much only. So it would be better if we can go through it again, as if we might not have missed something, but just
Okay.
to make sure that.
Okay, just to make sure that you might not have missed something. So
Yes,
when
sir.
I'll do this, might be I will go a little faster. And if you
Yes, sir.
find that there's some part that you have not done, just tell me, then I'll go that part slower.
Yes, sir. It will be good. Yes, sir. Yes, sir.
Huh?
Yes, sir.
So I'll do the recap and we'll go ahead and discuss. Fine. Let's stop today. Thank you.